So one of the things we're going to talk about in today's lesson is what solubility is and how we can identify which solubility, in fact, what a solubility factor can do to increase or decrease if something will dissolve or not. Then we'll talk about the solubility curve. So this first thing, before we get going into the actual lesson too far, I want to ask the question, what happens when you add energy to a system in terms of particles? So when you add energy to a system in terms of particles, what do the particles start doing? They start moving faster, right? And so that's going to be important to think about going forward in a minute here. Now, the other thing that I would like to talk about is the example that I kind of came up with is okay, all right. So you go on an elevator, right? And the elevator is at maximum human capacity of 9 human beings, okay? And the rule of the elevator says that all 9 human beings can only have one arm. So they all have one arm. Just hear me out. Now, at some point or another, though, the human beings, if I start adding 3 puppies to the elevator, each human being has the opportunity to pick up and hold 1 puppy because they only have 1 arm, okay? So if I add 3 puppies to the elevator, there is a 1 in 3 chance that the puppy will be picked up. Does that make sense? Sure. Because there's 9 people and 3 puppies, right? So if I add the 3 puppies, they get picked up. They have quote unquote dissolved into that system. Okay. If I add 3 more puppies, I can't. That means that there's 6 humans left over. And of those 6, 3 of them are going to grab the 3 new puppies. So now I have 6 puppies dissolved into the system. Does that make sense? And if I add 3 more puppies, right, that means there's only 3 humans left. And those 3 humans can pick up those 3 puppies. Okay. So now at this point, that elevator situation has in an equal number of puppies to human beings. And if I add 3 more puppies, those puppies cannot be picked up, so they're going to stay on the floor. Because remember, the humans only have 1 arm each. Okay? You follow me? So that's going to become important. That example I want you to think about, because we're going to talk about when you dissolve something, there is a specific amount of particle that can get dissolved in a specific amount of water. Okay, and that has to do something to do with solubility. So if there's in the human versus puppy example, Verfurth. Sorry. Okay. Ooh. So if there is there are a finite number of human beings in that example that can hold puppies. Does that make sense? And the same thing applies to water or a solvent and particles. There's only so many particles that can get dissolved in a given amount of water. Now, at a specific temperature, which is something we're going to talk about in a moment, if we are comparing 2 substances, sometimes you can add more of one substance to the water than you can of another substance. Now, I don't know about you, but in terms of stuffed animals, I can hold more than 1 stuffed animal in 1 arm, right? So if we change the puppies to stuffed puppies, right? Now the people in the elevator can, in theory, hold more puppies. So more puppies can be dissolved than the 9 people that are in there. So that's what this is kind of getting at. If more solute can be dissolved in the same amount of solvent, the solubility is said to be increased. If less solute can be dissolved in the same amount of solvent, the solubility is said to be decreased. So we're going to talk a little bit more about that in terms of how temperature can have an effect on it. So again, we're going to go back to the fact that we added temperature to the system, making the particles move faster. So in this instance, if we add temperature, what will happen to the solubility? So in this case, we're going to say that the solubility of particles will increase. Okay. And the evidence would be that as temp increases, more particles can dissolve. Now, the reasoning that one might be able to use for this is that adding energy causes intermolecular forces of attraction to be overcome. Okay, so adding energy between solute particles. And as a result, the solute particles can interact with the solvent particles. Okay, so that's kind of the gist of what happens with temperature. Now, if you increase the temperature of the system, the solubility of the system will increase. If you decrease the temperature of the system, the solubility will decrease. Okay. The next factor that can affect solubility is stirring or agitation. So, you know those drops of water flavoring. You know what I'm talking about? They come in like the triangle kind of shaped container, and you open up the water and you put the drops in, and it's a drop. Yeah, like Mio or whatever. You put the drops, and then you seal up the water, and then you got to give it a shake, right, and then you take another sip. You're like, needs a little bit more, so you put more drops in and you give it another little shake, right? So what that's doing is that's stirring or agitating that system, okay? And what that's really doing is it's allowing that substance, that Mio or whatever that substance is, to be distributed a lot faster amongst the entire system, or be dissolved in amongst the entire system faster. So by agitating, we can say that solubility will increase. And the claim, or the evidence rather here, will be the system. As the system is stirred, more particles can dissolve. So as the system is stirred, particles dissolve faster. And so our reasoning for this would be that now by mixing the system or stirring the system or agitating the system, the solute and the solvent particles are being forced to collide and interact with one another. So we'll say that. Solute and solvent particles are being forced to interact with each other. So if we're forcing them to interact with each other, they are more likely to form intermolecular forces of attraction with each other. Okay. So that's stirring and agitation. So if you agitate a system, you can increase solubility. The next one is crystal size, but I'm also going to refer to it as surface area. So you know that pink Himalayan sea salt that comes in the grinder, and you kind of grind it up to get the good stuff, right? But if you take the grinder top off, you got like these flakes or chunks of like pink Himalayan sea salt. You take one of those chunks and you chuck it in a bucket of water, it'll dissolve, but it'll take some time. Okay. If you put it back in the grinder and you grind it up, and when you put teeny tiny crystals of that salt in the water, what'll end up happening is it'll dissolve faster. So if the size of the crystal is increased, what will happen to the solubility? So in this case, we would say that solubility would decrease. Now, the evidence for this is that larger crystals tend to dissolve slower. And then our reasoning for this is because larger crystals tend to be formed with really, really strong intermolecular forces of attraction. So we'll start with that. So and as a result, those particles are more difficult to separate and eventually dissolve. Okay. So those are three factors that can affect solubility of a substance. And I realize that you're going to kind of go forward here and work, and we're going to go on to the next side of your note packet, which is we're going to talk about something called the solubility curve, which is one of my favorite graphs in all of chemistry. Happens to be one of my favorites. Just really like this one. So, solubility curve, here we go. Look at this graph. There's a lot of things going on in this graph, and as a result of that, we're going to kind of try to focus in on a couple of things. This problem is asking us to talk about or focus on NaNO3, so I'm just going to highlight that, and I'm going to talk about NaNO3 for a moment. That line on this graph tells me a lot of information about the sodium nitrate. So one of the things that I want to point out here is that the y-axis is grams of solute per 100 grams of water. So you have to kind of imagine that we've got this container and it's got about 100 grams of water in it. Okay. And what that means is that, like, I'm just going to pick a random temperature. I'm going to pick something like 20. Sure. We'll pick like 20, right? So if I go on 20 and I go up and over, it looks like I can put in about 87 grams of NaNO3. Okay. So at 20 degrees Celsius, I can dissolve 87 grams of NaNO3 in 100 grams of water. But if I heat the temperature up, So if I heat that 100 grams of water up to something like 60 degrees Celsius, it looks like I can put in more than 87. I can actually put in, I don't know, somewhere around 125. Okay. So if I heat up 100 grams of water, according to this graph, I can put in 125 grams of NaNO3. So I'll just draw that picture. So this is going to be, it's a 100 grams of water. And I'm going to say that I've got, 125, and that's here. Now, remember, the first one we said was at 20 degrees Celsius, and this one is at 60 degrees Celsius. Now, the interesting thing about this is that if you're at 60 degrees Celsius and you've added 125 grams of sodium nitrate, and you allow it to cool. So let's say we allow it to cool to 40. So we're going to do like this. So if I cool it down to 40, at 40, I can only hold like 105. So if I have 125 dissolved because I started it at a warm temperature and I allow it to cool down, that means that when I get to 105, some of that stuff that was dissolved before is going to recrystallize and no longer be dissolved. Okay. And what I mean by that is that roughly, what is that? 25, 50, like 20 grams of that is going to come out of solution. So when you cool something down, it becomes less soluble. It can hold less stuff. Does that make sense? Hopefully. Okay. Now we're going to really focus on this problem here to begin with. So, all right. Okay. So that's that. Okay. In this problem, we're looking at 40 degrees Celsius, which when I take that over is like 105. So at 40 degrees Celsius, I can put 105 grams of NaNO3 in, according to the graph, 100 grams of water. Okay. But the question is asking, what will happen if I want, or how many grams can I put in at 300 grams of water? So I will rewrite that statement here. So at 40 degrees Celsius, the question, I'm trying to figure out how many grams of NaNO3 can I put in 300 grams of water. Okay. So what I'm going to do is I'm going to make a relationship or a ratio or a proportion, actually. Let me speak proper math terms. So I'm going to take my 105 grams of NaNO3 and put it over 100 grams of water, because that's the relationship in this instance here. I'm then going to go ahead and set up my second part of this ratio of proportion, where I'm going to be solving for, I don't know, question mark, how many grams of NaNO3 would I be able to sink into 300 grams of water. So when you have something that looks like this, what math wizardry can you do?
Multiply 100, 3 times 300, and then divide by 100.
Cross multiply is what you're saying, correct? Yeah. So we can do that cross multiplication wizardry. And for those of you that need to see it, I'm going to write it out real quick once. So if I have 105 grams of NaNO3 times 300 grams of water, that's going to equal 100 grams of water. And we're really trying to figure out question mark grams of NaNO3. So we grab our calculator and we put that in our calculator. So 105 times 300 and then divide it by 100. And your final answer here should be somewhere in the ballpark of 315 grams of NaNO3. questions about this so far? Okay. So the next one, the next example problem has to do with a different substance. Okay. And so, but it's a different substance that's on the solubility curve. And so in this instance here, I'm going to be looking at the relationship between potassium nitrate um, and what I can do with that one. So I'm going to try to focus on potassium nitrate here, and I'm going to take a highlighter and I'm going to highlight that line, and I'm going to focus on potassium nitrate. Looks something like this. And then I'm going to go ahead and read the graph with my given information. So we're really talking centering around 50 degrees Celsius. So I'm going to go up, over. So at 50 degrees Celsius, 80 grams of KNO3 can dissolve in, again, 100 grams of water. Okay. So then the question is asking us is at 50 degrees Celsius, if I have 150 grams of KNO3, how much water will I need to dissolve all of it? So question mark, grams of water. So we're going to set up a very similar proportion. So 80 grams of KNO3 over 100 grams of water. And I have my 150 grams of KNO3 over, in this case, question mark, grams of water. We're going to cross multiply again. And for those of us that need to see it, I'm going to write it out. So I'm going to have 80 grams of KNO3 times question mark grams of water equals 100 grams of water times 150 grams of KNO3. So again, we're going to grab our calculator, going to do some math. 150 times 100, that answer divided by 80 with the appropriate number of significant figures, that's going to be about 187.5. So I'm going to make it 188 grams of water. And actually, yeah, should really be 190. I lied.
Why would it be 190?
Well, because the 80 only has two sig figs, 80 with a decimal, it really should be like 188, but like, or 187 exactly, but like 190 sig figs and all that fun stuff. All right. So the next one is a U try, right? I want you to do number 3. Let's give it the old GHS try, and I believe in you. You can do it. Okay, so for those of you that work through this one, in this instance here, we have 50 grams of KCl and 100 grams of water, and we're trying to figure out how much KCl we can put in 250 grams of water. So I did some cross multiplication, and I got 125 grams with significant figures. Then I rounded it to 130, but really, in reality, it's about 125 grams. Pardon?
How did you get 100 for the first one?
So the question is, how did I get 100 for the first one? And this label right here tells me that it's the number of grams in 100 grams of water. So for all of these problems, when you're reading off of this chart,
the first one will always be 100.
Yes.
Okay.
Well, I mean, for this chart, like if we give you a different chart that has a different value on the side, you have to be aware of that.
Okay.
Okay. So the last thing that we need to talk about real quick once is comparing the solubility of substances on the same curve at the same temperature. Okay. So what that means is if I'm looking at the relationship now between, say, KCl and KNO3. Okay. So I'm going to take a look at KCl. So I have, I'll highlight KCl here, and I'm going to highlight KNO3 here. And then we are, in this one, we are looking at it at 30 degrees Celsius. So if I go 30 degrees Celsius, I cross KCl there and I cross KNO3 here. Okay. So it looks like KCl can hold about, 35 grams of KCl at 30 degrees Celsius, and and KNO3 can hold about, 47 grams of KNO3 at 30 degrees Celsius. So that means KNO3 is more soluble at 30 degrees Celsius than KCl is. If I look at the second example here, I'm going to compare KCl and I'm going to compare NH4Cl. So in this substance here, but we're working at 70 degrees Celsius. So if I go up here, we cross KCl's line right around there, and we cross NH4Cl's line right about there. So it looks like NH4Cl can hold 60 grams of dissolved solute and at 100 or at 70 degrees Celsius, and KCl can hold about, 55 or 45 grams. So that tells me that NH4Cl is more soluble. And then the last question that we're gonna really address here is looking at the solubility curve. So looking at this entire graph, what is the least soluble solid, or what is the least soluble solute at 10 degrees Celsius? So all I did is went to 10 degrees Celsius and I just drew a line all the way up to the top. And in terms of least, it's going to be the one that I cross first going up. So that tells me that my answer at 10 degrees Celsius, the least soluble, is KClO3. Okay. So that sums up today's lesson. Anybody have any questions about reading the solubility curve? All right, then that wraps this one up.